Electrical distribution, wiring types. Wire types for North American wiring practices are defined by standards issued by Underwriters Laboratories, the Canadian Standards Association, the American Society for Testing and Materials, the National Electrical Manufacturers Association, and the Insulated Cable Engineers Association. Most circuits in the modern North American home and light commercial construction are wired with non-metallic sheathed NM cable designated type, often referred to by the brand name Romex. This type of cable is the least expensive for a given size and is appropriate for dry, indoor applications. Conductor materials. As discussed previously, we are dealing with copper, absolutely the best conductor in common use as it has low electrical impedance, so a relatively small conductor can deliver a lot of power over long distances without too much power loss or heat generation. We have tinned copper, still sometimes seen on older properties. Copper is tinned for two reasons: to aid soldering and to stop the copper from reacting with old rubber insulation. We also have aluminum, a good conductor of electricity, but has higher impedance to the flow of electrons, which means that larger conductors need to be used for any given amperage. Aluminum was used for residential branch circuit wiring from the mid-1960s to the late 1970s, but was found to be unreliable. We'll explore this later. We have copper-clad aluminum. Coating aluminum in copper was an attempt to overcome the issue of oxidization of the aluminum conductors that was leading to failures. It did not have the failures associated with pure aluminum and is considered safe. However, copper-clad should be sized the same as normal aluminum. Tinned copper is often mistaken for single-strand aluminum wiring, but is given away by its rubber insulation, as well as the cut copper ends, which can sometimes be observed upon closer examination. One will never find aluminum wiring with anything other than plastic insulation in residential construction. Knob and tube. Knob and tube wiring is so named because of the porcelain fittings used to support and insulate the conductors from the timber components in the home. The knob holds the wire away from rafters and joists, while the tubes are inserted into holes bored through joists and studs to protect the conductor and its rubber insulation. Knob and tube wiring was the common method used to wire homes in the United States prior to 1930. Knob and tube is a two-wire system with a hot, ungrounded, and a neutral, grounded conductor only. No separate ground is used, so all receptacles would have been two-prong only. The home inspector should report any knob and tube wiring as in need of further evaluation by an electrical contractor due to the following reasons. 1. The insulation is often very brittle and leaves conductors exposed when disturbed. 2. All circuits are ungrounded, which will not suit many modern electronics, such as computers, televisions, and stereos. 3. The conductors are often buried in attic and wall insulation. This is a problem as they were designed to work in free air. 4. The wire gauge is commonly 14 AWG only, which is not sufficient for most modern household needs. 5. It's very common for knob and tube wiring to have been added to over the years, and it may contain many splices outside of approved enclosures. Originally, joints in knob and tube were all spliced, soldered, and tapped outside of enclosures. Armored cable, or AC. Conductors protected by a spiral-wound outer metal sheathing have been around since the early part of the century, and they gained wide acceptance in the 1930s, especially after the NEC's acceptance in the 1932 code. Several types of AC cable exist, and they are not all the same. The earliest type was introduced by General Electric under their brand name BX. Many people still wrongly call all type AC cables by this name. Type AC cables fall into two categories: those with an internal bonding conductor and those without. In many cases, the sheathing itself or its internal bond has been used improperly as the grounding conductor, or even worse, as the neutral conductor. As of 1959, the NEC has required that all type AC cable includes a bonding strip which connects all the individual convolutions. The older BX cable did not have this, and the exterior metal casing was not meant to be an effective fault current path. Since the 1960s, a newer type of AC cable assembly came onto the market. The improved MC cable includes a proper grounding conductor. Exterior flexible conduit. This is often seen by the home inspector as the supply conduit to outside installations, such as air conditioning compressors. This ACBX type conduit has a PVC outer sheathing to render it watertight, which should be marked UF for exterior use. It is not approved for direct burial, however. Rigid conduit. Different types of rigid conduit are available for different applications, and some are more common in some regions than others. The three primary types used are EMT, thin wall. This is electrical metal tubing, which can be bent to shape for installation. RMC, thick wall. This is threaded rigid metal conduit, where any changes of direction require angled fittings. RNC/PVC conduit, often referred to as Schedule 40 or 80 plastic. This gray-colored rigid non-metallic conduit is very common in newer construction, but should not be confused with white or ivory-colored PVC piping, which is not rated for electrical use. Non-metallic cable, or NM. Many people use the name Romex when referring to type NM cable. Romex is a trademarked name that has come into common usage for referring to plastic-covered wires, but type NM just means non-metallic and also applies to other cable styles. The earliest NM cables were, in fact, rubber-insulated copper conductors bound together as an assembly with a woven cloth sheathing. Originally approved by the NEC in 1928 as a replacement for knob and tube wiring, it became the most common residential wiring used from the late 1940s up to the introduction of modern thermoplastic Romex-type wiring of the early 1960s. Prior to 1985, standard NM was rated for 60-degree applications, which was increased to 90 degrees and is now marked NM-B. In type NM cable, conductor insulation is color-coded for identification, typically one black, one white, and a bare grounding conductor. The National Electrical Code, or NEC, specifies that the black conductor represent the hot conductor with significant voltage to earth ground, the white conductor represent the identified or neutral conductor near ground potential, and the bare/green conductor, the safety grounding conductor not normally used to carry circuit current. Aluminum wiring. According to the InterNACHI Home Inspection Standards of Practice, a home inspector is required to report upon single-strand solid conductor aluminum branch circuit wiring if observed by the home inspector. Between approximately 1965 and 1973, single-strand aluminum wiring was sometimes substituted for copper branch circuit wiring in residential electrical systems due to the sudden escalating price of copper. After a decade of use by homeowners and electricians, inherent weaknesses were discovered in the metal that led to its disuse as a branch wiring material. Although properly maintained aluminum wiring is acceptable, aluminum will generally become defective faster than copper due to certain qualities inherent in the metal. Neglected connections and outlets, switches, and light fixtures containing aluminum wiring become increasingly dangerous over time. Poor connections cause wiring to overheat, creating potential fire hazards. In addition, the presence of single-strand aluminum wiring may void a home's insurance policies. Inspectors may instruct their clients to talk with their insurance agent about whether the presence of aluminum wiring in their home is a problem that requires changes to their policy's language. Facts and figures. On April 28, 1974, 2 people were killed in a house fire in Hampton Bays, New York. Fire officials determined that the fire was caused by a faulty aluminum wire connection at an outlet. According to the Consumer Product Safety Commission, or CSPC, homes wired with aluminum wire manufactured before 1972, or old technology aluminum wire, are 55 times more likely to have one or more connections reach fire hazard condition than a home wired with copper. Aluminum as a metal. Aluminum possesses certain qualities that, compared with copper, make it an undesirable material as an electrical conductor. These qualities are as follows. Higher electrical resistance. Aluminum has a high resistance to electrical current flow, which means that given the same amperage, aluminum conductors must be of a larger diameter than would be required by copper conductors. Less ductile. Aluminum will fatigue and break down more readily when subjected to bending and other forms of abuse than copper, which is more ductile. Fatigue will cause the wire to break down internally and will increasingly resist electrical current, leading to a buildup of excessive heat. Galvanic corrosion. In the presence of moisture, aluminum will undergo galvanic corrosion when it comes into contact with certain dissimilar metals. Oxidation. Exposure to oxygen in the air causes deterioration to the outer surface of the wire. This process is called oxidation. Aluminum wire is more easily oxidized than copper wire, and the compound formed by this process, aluminum oxide, is less conductive than copper oxide. As time passes, oxidation can deteriorate connections and present a fire hazard. Greater malleability. Aluminum is soft and malleable, meaning it is highly sensitive to compression. After a screw has been over-tightened on aluminum wiring, for instance, the wire will continue to deform or flow even after the tightening has ceased. This deformation will create a loose connection and increase electrical resistance in that location. Greater thermal expansion and contraction. Even more than copper, aluminum expands and contracts with changes in temperature. Over time, this process will cause connections between the wire and the device to degrade. For this reason, aluminum wires should never be inserted into the stab, bayonet, or push-in type terminations found on the back of many light switches and outlets. Excessive vibration. Electrical current vibrates as it passes through wiring. This vibration is more extreme in aluminum than it is in copper, and as time passes, it can cause connections to loosen. Identifying aluminum wiring. Aluminum wires are the color of aluminum and are easily discernible from copper and other metals. Since the early 1970s, wiring device binding terminals for use with aluminum wire have been marked CO/ALR, which stands for Copper/Aluminum Revised. Look for the word aluminum or the initials AL on the plastic wire jacket. Where wiring is visible, such as in the attic or electrical panel, inspectors can look for printed or embossed letters on the plastic wire jacket. Aluminum wire may have the word aluminum or a specific brand name, such as Kaiser Aluminum, marked on the wire jacket. Where labels are hard to read, a light can be shined along the length of the wire. When was the house built? Homes built or expanded between 1965 and 1973 are more likely to have aluminum wiring than houses built before or after those years. Options for correction. Aluminum wiring should be evaluated by a qualified electrician who is experienced in evaluating and correcting aluminum wiring problems. Not all licensed electricians are properly trained to deal with defective aluminum wiring. The CPSC recommends the following two methods for correction for aluminum wiring. 1. Rewire the whole home with copper wire. While this is the most effective method, rewiring is expensive and impractical in most cases. Or 2. Use copolymer crimps. The crimp connector repair consists of attaching a piece of copper wire to the existing aluminum wire branch circuit with a specially designed metal sleeve and powered crimping tool. This special connector can be properly installed only with the matching AMP tool. An insulating sleeve is placed around the crimp connector to complete the repair. Although effective, they are expensive, typically around $50 per outlet, switch, or light fixture. Although not recommended by the CPSC as methods of permanent repair for defective aluminum wiring, the following methods may be considered. Application of antioxidant paste. This method can be used for wires that are multi-stranded or wires that are too large to be effectively crimped. Pigtailing. This method involves attaching a short piece of copper wire to the aluminum wire with a twist-on connector. The copper wire is connected to the switch, wall outlet, or other termination device. This method is effective only if the connections between the aluminum wires and the copper pigtails are extremely reliable. Pigtailing with some types of connectors, even though underwriters' laboratories might currently list them for the application, can lead to increasing the hazard. Also, be aware that pigtailing will increase the number of connections, all of which must be maintained. Aluminum Wiring Repair, AWR Inc., of Aurora, Colorado, advises that pigtailing can be useful as a temporary repair or in isolated applications, such as the installation of a ceiling fan. CO/ALR connections. According to the CPSC, these devices cannot be used for all parts of the wiring system, such as ceiling-mounted light fixtures or permanently wired appliances. As such, CO/ALR connections cannot constitute a complete repair. Also, according to AWR, these connections often loosen over time. Alumicon. Although AWR believes this method may be an effective temporary fix, they are wary that it has little history and that they are larger than copper crimps that are often incorrectly applied. Replace certain failure-prone types of devices and connections with others that are more compatible with aluminum wire. Remove the ignitable materials from the vicinity of the connections. Aluminum wiring can be a fire hazard due to inherent qualities of the metal. Inspectors should be capable of identifying this type of wiring. Repair methods. Since the early 1970s, several methods have been tried to improve the contact between aluminum wire and junctions and receptacles. The single biggest issue is that it is very difficult for a contractor to know where all of the hidden junction boxes are in an older home. Rewiring in copper. This is obviously the best choice by far, as it completely replaces the aluminum branch circuit wiring. However, this is very costly and disruptive. Pigtailing copper. A method many electricians tried was to pigtail a piece of copper wire onto the aluminum using a wire nut. There were even special purple wire nuts produced with antioxidant paste in them designed for this application. However, this repair did not work as intended, as wire nuts are not able to overcome the expansion problems of aluminum. This is not considered an effective repair. CO/ALR switches and receptacles. These were designed to replace previous CO/AL receptacles, as they had a higher quality conductor lug assembly. However, this addresses only the issues of switches and outlets, but not the connections and boxes. This is not considered an effective repair. Coupolum connectors. These are the recommended upgrade for aluminum wiring. A special crimp connector and crimping tools are used to pigtail a piece of copper wire onto the aluminum conductor. It is then covered with a heat-shrunk insulation. This is the only CPSC-approved repair, but some connections still may be inaccessible. Branch circuit connections. Evaluating in-panel wiring. The purpose of this section is to look in more detail at the connections themselves inside the panel. We have already discussed the panel connections and the breaker/fuse issues, but there is still much to inspect. Probably the most common electrical defect that an inspector will report is double tapping of fuses and breakers, but there are many other connections that may also be incorrect. Conductor sizing. One of the first things the inspector should evaluate is the size of the conductors relative to the amperage rating of the fuse breaker. As we have seen, if the breaker is rated for 30 amps but the conductor is a 14 AWG rated for 15 amps, we are likely to see the conductor overheating and potentially starting a fire. Bear in mind that there may be exceptions under special conditions. For example, the NEC allows 12 AWG on a 30 amp under 240.4E or G. A nameplate on an AC unit or a specific motor load may indicate such exceptions to the standard rules. Please refer to the table in the Branch Circuit Connections section of the How to Perform Residential Electrical Inspections course for the most common conductor sizes used in residential branch circuits, along with their maximum permitted breaker or fuse sizes. Aluminum single-strand wiring should always be deferred to a licensed electrical contractor for an inspection. Double tapping. Double tapping is sometimes also called double taps or double lugging. This is when there are two conductors terminating under a screw or lug which is rated for only one. The problem here is that each conductor will not have enough contact area against the screw or its lug, which may lead to arcing and overheating of the conductors. These should always be fully evaluated, as there are a couple of exceptions. Breakers rated for two conductors made by Cutler hammer and square D, and conductors spliced together and pigtailed into a breaker or fuse. Neutrals sharing lugs. As the neutral is also a current-carrying conductor, the neutrals should each be terminated separately on the neutral bus. An inspector will often find signs of arcing and overheating where any multiple conductors share a common lug. This condition is basically just another double tapping situation. Unrated conductors. The inspector will often see homeowner wiring using things like doorbell or speaker wire and cut down extension cords supplying circuits derived from the panel. This is always unacceptable and should be replaced by a licensed electrician. Nicked conductors. Any conductor that has been nicked, as in cut, scratched, incised, or damaged, as the insulation was removed, is now of a smaller diameter than intended and has a higher resistance to the flow of electrons. This higher impedance is just the same as having too small a conductor on the circuit, since the damaged area will be the weak link and may either act as the fuse or overheat. Antioxidant paste. This grayish paste is commonly found on older aluminum multi-strand conductors and is still required by some city electrical inspectors. This paste was designed to stop the aluminum from oxidizing and thus be better able to maintain a clean contact footprint in its lug. Interestingly, the NEC has never required its use. Rather, they have permitted it. The alloys used in aluminum wire have greatly improved since the early 1980s, and while many manufacturers used to recommend its use in their conductors, few do so now. Abandoned wiring. All abandoned wiring should be removed from the electrical panel, or at the very least it should be properly isolated so that the conductors are not able to make contact with any live components. Arcing and overheating. As we have seen, any of the conditions covered may cause overheating to the conductors. The inspector should recommend further evaluation of any wiring that is in any way deficient, as failures can and do lead to fires, which can lead to loss of life. Splices in panels. While electrical splices in panels are not in and of themselves improper, the home inspector should bear in mind that, like double taps, they are the line of least resistance and often done by unqualified persons. Generally untidy panel wiring, double taps, lots of splices, and wire nuts are indicative of homeowner wiring, which probably requires further evaluation. Lightning damage. Occasionally, the inspector will open a panel and see most or all of the neutral conductors fired. This may have been caused by the property having been struck by lightning. The neutrals will be most affected by this since they are, of course, connected to the grounding system. Many times these conditions go unnoticed. A panel that has been hit like this should be fully evaluated. Protection of wiring. Conductor protection. All current-carrying wiring needs some form of protection from mechanical damage. Also, the occupants of the home need protection from potential shocks where wires are spliced together. Exposed wiring. Obviously, there should be no exposed wiring in the finished or livable areas of the home, but this means that some unfinished areas may have exposed non-metallic Romex-type cables. In this section, we will look at those areas and discuss what is and is not acceptable. The guidelines in this section are based on current adopted NEC codes and may not be applicable in your area, or may not apply to an older property. Remember, code is based on previous failures that have produced unsafe conditions. Exterior wiring. The home inspector should report any exposed wiring at the exterior, especially interior type wiring such as Romex types, which are not rated for exposure to ultraviolet light, also known as sunlight, Also, any exterior conductors should be protected against mechanical damage to a height of 8 feet. Crawlspace and basement wiring. In most jurisdictions, exposed wiring is allowed in basements and crawlspaces. In the northern U.S., we commonly see Romex conductors unprotected as they leave the panel, and the circuits generally run unprotected on the ceiling joists. Crawl spaces are the same unless a prohibitive condition exists, such as a very damp area, then exposed cable assemblies are the norm. According to the 2008 NEC, crawl spaces and unfinished basements that have NM cable installed shall be drilled through the joists unless installed on a running board. Cables with 3 8 AWG or 6 AWG and larger shall be allowed on the surface of the joists. Attic wiring. Although exposed conductors are allowed to run in attics, there are some safety concerns that the home inspector needs to be aware of, especially as the homeowner is going to enter the attic space to store seasonal goods. All conductors should be protected within 6 feet of the scuttle opening. This means that no cables should be run on top of joists in this area. This dimension also includes the underside of roof framing rafters. If they run perpendicular to the joist, they should either be drilled through the timbers and have a running board over the top, or be stapled to the side of a running board. Wiring in cabinetry. The home inspector will often see unprotected wiring in undersink locations, especially supplying waste disposals. If any hardwired appliances have exposed conductors, they should be protected with metal spiral armoring. Protection of wiring through studs. In frame construction, all of the home's conductors must run through the wall stud work to supply the outlets. These hidden conductors need to be protected from accidental damage. Most frame homes are built with either timber or steel studs, and each have separate protection requirements. For timber studs, any cable assemblies closer than 1 1/4 inches from the front face of the stud need to be protected from damage from drywall screws and the homeowner hanging pictures, etc. This is achieved by installing a nailing plate on the stud. Note that the 1 1/4 inches applies to both sides of the stud if the required distance is not maintained. For steel studs, where NM cable or electrical non-metallic tubing is run through openings in steel studs, protection against penetration is required. A steel sleeve, steel plate, or steel clip not less than 1/16 of an inch in thickness shall be used to protect the cable or tubing. An opening in the stud requires a plastic bushing to protect the cable from chafing against the steel's raw edge. This protection must encircle the entire opening and not just the bottom half. Support of cables and conduits. All cables, cable assemblies, and conduits need regular support from the structure. The home inspector will often see great lengths of Romex and other conductor types strung unsupported through crawl spaces and attics. This again is indicative of homeowner work and needs correcting. The basic specifications for supports are outlined here. NM/Romex cables stapled within 12 inches of metal enclosures and 8 inches from plastic gang boxes, and every 4 feet and 6 inches of run length. AC cables stapled within 12 inches of metal enclosures and every 4 feet and 6 inches of run length. MC cable has a run length that is extended to 6 feet between the required supports. Metal conduit/EMT clamped within 36 inches of enclosures and every 10 feet of run length. Protection of personnel. Exposed wiring, and especially exposed splices and connections, are obviously a danger to the home's inhabitants. All connections in conductors need to be made in approved enclosures, typically panel boards, junction or J-boxes, and gang boxes. A gang box is what is behind switches and receptacles. The home inspector should report any splices or other connections that can be seen either outside of enclosures or in enclosures where the cover plate is missing. All enclosures and J-boxes should also have proper cable connectors where the conductors enter the box. Plastic gang boxes do not require these since strain relief is built in. 120-volt terminations. 120-volt receptacles. The term receptacle actually covers all types of applications, whether they are light fixtures or wall outlets. Every habitable space in the home is required to meet minimum standards of power and lighting availability. Never install a switch receptacle fully inside of a room where both the top and bottom of the duplex is controlled by a switch. A switched receptacle may be acceptable to meet the 210.70A1 Exception 1 for using a receptacle to meet the lighting outlet requirement in rooms other than bathrooms and kitchens. It will not meet the 210.52A1 wall spacing requirements. In this section, we will look at the current standards for outlets around the home and the methods for testing them. Many older homes, however, will not have what would now be the required number of outlets. This would not necessarily be a defect, but the home inspector would be well advised to point out to the homeowner or home buyer that there may not be enough outlets to suit a modern family's needs. Homes with many appliances connected through extension cords are typical of properties built with insufficient outlets. Habitable spaces. All habitable spaces are required to have electrical power and, in new construction, one would expect to see an outlet at every 12 feet of wall space. Even hallways longer than 10 feet are required to have power. Floor-mounted receptacles. Standard wall-type receptacles pose a danger when mounted horizontally in a floor structure. Dirt, dust, and any spilled water will affect the outlet, plus children or pets will always play with anything on the floor. Recommend upgrading floor receptacles to the approved type with special covers. Service locations. Any unfinished space that houses serviceable equipment, such as furnaces and air handlers, is required to have not only a light but also a power outlet. This includes attics and crawl spaces. Kitchen circuits. All kitchens are required to be supplied by two 20-amp circuits over and above any requirements for dedicated outlets for stoves, etc. These circuits shall not serve any lighting needs. One of these branch circuits should be used for small appliance receptacles no more than 20 inches above the countertop. These outlets must also be GFCI protected. The minimum two 20-amp circuits shall both supply receptacles serving the countertop space. As of the adoption in 2002 by the NEC, all kitchen receptacles installed in a new construction are required to be GFCI protected. All counter spaces wider than 12 inches should have an outlet, and the maximum distance between outlets should be no more than 4 feet. There should also be a receptacle within 2 feet of each end of the counter ends and from any break in the countertop, such as for a range, refrigerator, and sinks. Islands and peninsulas are also required to have at least one receptacle to serve the countertop space. If the space is not available on the countertop area, the NEC allows the receptacle to be installed below the countertop surface, which must not be more than 12 inches below the countertop and not installed under any overhang 6 inches or more from the base of the island or peninsula to the edge of the overhang. No countertop outlets are allowed to be installed face up in the horizontal surface. When dealing with the space behind a corner-mounted sink or corner-mounted cooking unit, the 2008 NEC requires that if such space is less than 18 inches, it is not considered a wall space. If that space is 18 inches or more, it must meet the same spacing requirements previously discussed. A countertop with an extended face sink or counter-mounted cooking unit, such as when that counter sticks out and creates a space behind the sink or cooking unit, is not considered counter space if that space is less than 12 inches. If that space is 12 inches or more, then that space must meet the same spacing requirements previously discussed. When dealing with islands and peninsulas, the 2008 NEC requires that where a range, counter-mounted cooking unit, or sink is installed in an island or peninsular countertop, and the width of the countertop behind the range, counter-mounted cooking unit, or sink is less than 12 inches, the range, counter-mounted cooking unit, or sink is considered to divide the countertop space into 2 separate countertop spaces. This would mean both sides would need a receptacle to meet current codes. Most jurisdictions require dishwashers and waste disposals to be on dedicated circuits. Often, refrigerators are plugged into dedicated outlets, which is allowed by the NEC to prevent nuisance tripping from installed GFCIs. Bathroom circuits. In newer homes' bathrooms, outlets are required to be on dedicated 20-amp GFCI protected circuits, and at least one receptacle is required to be installed within 3 feet of any vanity basin. The home inspector is justified in suggesting that non-GFCI receptacles in older bathrooms should be upgraded for safety reasons. There is also a common misconception that no switches or receptacles may be installed within 3 feet of a bath or shower enclosure. This is correct for Canada, but not a requirement in the United States. Laundry rooms. There must be a minimum of one 20-amp circuit within 6 feet of the appliance location. Dryer outlets will be covered in the 240-volt section, but they should have a 4-wire, 30-amp minimum supply. Garage receptacles. Garages were required to have a minimum of one GFCI outlet, and inspectors may find that they also have non-GFCI receptacles dedicated to appliances such as door openers and extra refrigerators and freezers. Lighting is also required. However, be aware that under the 2008 NEC, the exceptions that allow dedicated receptacles for specific appliances were removed. Now, all receptacles in garages and unfinished basements must be GFCI protected, including sump pumps. The only exceptions are for fire alarm and burglar alarm systems, and receptacles outside installed for roof snow melting equipment. Exterior receptacles. Newer homes are required to have a minimum of one outlet at the front and another at the rear. These receptacles are required to be weather-tight while in use and GFCI protected. Recommend upgrading of the older receptacles, as this is a safety enhancement that should be considered. Non-GFCI outlets are allowed for dedicated single outlets only, such as one will find supplying heater strips in colder climates. Visual inspection. The inspector should visually inspect a representative number of receptacle outlets and report the following: 2-wire only circuits, damaged or missing cover plates, missing screws, damaged receptacles, signs of overheating on receptacles or surrounding walls, and lack of GFCIs and AFCIs. Inspecting receptacles. Branch circuit outlet testing. The standards of practice requires that the inspector inspect a representative number of receptacles, including those deemed to be GFCI and AFCI protected. It's a good idea to check every receptacle that can be physically accessed that does not have something plugged into it, as well as every GFCI or AFCI protected circuit. Before exploring these protocols, we must understand how receptacles should be correctly wired. A receptacle has the following characteristics. Small slot is the hot or ungrounded supply. Large slot is the neutral or grounded return. And round pinhole is the grounding conductor. This is very important if the receptacle has reversed polarity, hot and neutral switched, because then things like lamp holder collars may become live and pose a great electrocution hazard. It is very common to find 3-prong receptacles with no ground, or worse, receptacles with a false or bootleg ground where the grounding terminal has been illegally connected to the neutral. Circuit testers. There are many different types of circuit testers available, starting with very basic continuity testers, which cost a few dollars, up to full function testers, which cost several $100s. The differences between the various models are what they are able to test for and how they display the results. It is good practice for an inspector to have and use a receptacle tester with a GFCI and AFCI test button. The functionality of some common testers can indicate open ground, open neutral, open hot, hot ground reversed, hot neutral reversed, normal, GFCI trip, bad or high resistance ground, AFCIs for proper operation, GFCIs for proper operation, shared neutrals, and correct wiring. False grounds. Sometimes referred to as bootleg grounds, false grounds occur when the grounding terminal on the receptacle has been improperly connected to the neutral. Most testers will not be able to read this condition, as the grounds and neutrals are correctly terminated together in the panel anyway. The inspector should be suspicious of older style wiring in the panel that tests like a grounded circuit at the receptacles. It is very common to find an old home with 2-wire conductors upgraded to 3-prong outlets where the ground has been faked. This can lead to very dangerous conditions downstream of the receptacle with the illegal connection, especially should there be any wiring or appliance failure. Voltage drop. Some inspectors are now starting to check voltage drop along conductors. This falls well outside of industry standards of practice, but with electrical components becoming ever more sensitive to voltage fluctuations, many more inspectors will start to check for this. Also, voltage drop can be indicative of too many outlets on a circuit, poor connections, or undersized conductors on long wiring runs, all of which could lead to overheating and failures. The National Electrical Code recommends that voltage should not drop more than 3% on branch circuits and a 5% overall drop, including the service itself. Ungrounded 2-prong receptacles. 2-prong receptacles, often found by an inspector in an older home, that are connected to 2-wire cables do not have the ground wires, which protect people and electrical devices in case of a fault. It is possible to retrofit a new 3-prong or GFCI receptacle into the same receptacle box without any rewiring, as long as the box itself is grounded. Metal boxes attached to armored or BX cable, which is a type of wiring commonly found in old homes, are typically found to be properly grounded. The armored or BX cable's flexible metal jacket serves the same purpose as a dedicated ground wire. If the box is not grounded, a GFCI can be installed or an electrician can be hired to fix the wiring. Simply replacing an older 2-prong outlet with a 3-prong outlet can be hazardous because the receptacle will appear to be functional with a ground, but in fact there isn't one. If someone were to plug a faulty 3-prong device into that fake grounded receptacle, a shock hazard is very likely. Electricity moving through the device casing would create an energized surface from which a person could be electrocuted. Another problem with replacing ungrounded 2-prong receptacles with 3-prong ones is in relation to surge protection device, which relies on a solid ground to route any transient activity. The ungrounded receptacle would not be able to protect the device from a surge. It is permissible to replace a 2-prong ungrounded outlet with a 3-prong GFCI outlet, but it must be labeled as GFCI protected outlet, no equipment ground. Even though there is not a grounding conductor, there is still some protection against shock provided by the GFCI. If an inspector has doubt as to what is being inspected, a qualified electrician should be consulted. Inspection recommendations. The home inspector should check the following conditions on a representative number of receptacles: no power present, no ground, open neutral, reversed polarity, hot and neutral, and reversed ground and hot. The inspector may also choose to invest in equipment to enable them to report on low resistance grounds, bootleg grounds, true voltage, and voltage drop. 240 volt terminations. 3-wire appliances. Prior to the adoption of the 1996 NEC code revisions, 3-wire 240 volt supplies were common. The cable assembly carries 2 120-volt ungrounded or hot conductors and 1 grounded or neutral conductor. As there is no separate grounding means in this installation, the metal frame of the appliance was allowed to be bonded to the neutral. This is no longer allowed in new construction. 4-wire appliances. Since adoption of the 1996 NEC, all 240-volt circuits are required to be 4-conductor assemblies carrying 2 120-volt ungrounded or hot conductors, 1 grounded or neutral conductor, and 1 equipment grounding conductor. Some appliances still have the bond between the cabinet and the neutral, and this needs to be removed when used on a 4-wire circuit. If a 3-wire configuration exists and one wishes to extend the circuit, for example in a renovation, it would be considered a new installation and must be rewired in a cable with 4 conductors. Receptacle blade patterns. There are many odd receptacle styles out there, but the 2 that are most common around the home are dryer outlets. A 240-volt clothes dryer receptacle has 4 prongs. The top prong is round and is for the ground connection. The bottom prong is shaped like an L and is for the neutral wire. The 2 vertical slots on the sides are for the 2 hot wires. Range outlets. A 240-volt oven receptacle also has 4 prongs, but the neutral prong is straight and not L-shaped. It is, however, narrower and thicker than the hot wire prongs. These 2 plugs have 4 prongs because they use 2 hot wires to provide the 240-volt power. These receptacles have different designs so that a 30-amp dryer cannot be accidentally connected to a 50-amp range circuit, for example. GFCI, Ground Fault Circuit Interrupters. Standards of Practice. The InterNACHI Home Inspection Standards of Practice, found at www.nachi.org/SOP, requires the inspector to inspect all ground fault circuit interrupter receptacles and circuit breakers observed and deemed to be GFCIs using a GFCI tester where possible. History. Since the early 1970s, GFCIs have been required in an increasing number of damp and wet locations. Recently, this requirement has been extended to all receptacles in garages. Because they are safety devices, the home inspector should check every installed GFCI circuit and may advise the client of areas where they should also be installed. Charles Dalziel, a professor of electrical engineering at the University of California, invented the ground fault circuit interrupter, or GFCI, in 1961. He came to realize that a common cause of death was the result of ordinary household circuits malfunctioning in the ground fault. His research objective then became to create a device that would interrupt a ground fault current before it became large enough to cause human physiological damage. The sensitivity, speed of action, reliability, small size, and cost required made the device almost impossible to design. However, in 1965, Dalziel received a patent for a ground fault current interrupter that would interrupt current before it grew to 0.005 of an ampere, which was small, reliable, and inexpensive. The device was based on a magnetic circuit plus a then newly developed semiconductor device. Most of the time, his invention does nothing. It just monitors the difference in the current flowing into and out of a tool or appliance. But when that difference exceeds 5 milliamps, an indication that a ground fault may be occurring, the GFCI shuts off the flow in an instant, in as little as 0.025 of a second. How does a GFCI work? GFCIs are designed to sense any difference in current between the supply on the ungrounded or hot conductor in a circuit and the grounded or neutral conductor. If the circuitry recognizes a differential of more than 5 milliamps nominal between supply and return, a solenoid trips open the circuit, causing all power to be disconnected. For this reason, a GFCI breaker or a correctly wired GFCI receptacle can protect all outlets farther downstream. Types of GFCI devices. There are 4 basic types of GFCI in common usage, and 2 or 3 of them are common in residential construction. They are 1. GFCI breakers in the distribution panel, 2. GFCI receptacles at in-home locations, 3. Stand-alone GFCIs as sometimes used with pools, and 4. Extension cords with built-in protection primarily found on construction sites. GFCI on 2-wire circuits. There is a common misconception that GFCIs work only on grounded circuits. This is not entirely the case. While there are conductors under which the GFCI will not be able to trip without a ground, the inspector should still recommend that any circuits in potentially wet or damp locations be fitted with them as a safety precaution. GFCI requirements. Refer to 2021 IRC E3902. Bathroom. To protect people, ground fault circuit interrupter GFCI protection should be installed in all bathrooms with 125 volt to 250 volt single phase 15 and 20 ampere receptacles. All bathroom receptacles. A bathroom is not necessarily a room. It is any area that includes a lavatory or wash basin and a water closet or toilet and a tub and/or a shower. There are no exceptions for GFCI requirements in bathrooms. All bathroom receptacles would include, for example, a receptacle in a light fixture, a receptacle in a clothes washer, or a receptacle for any appliance installed in a bathroom. Bathtub and shower stall receptacles. All 125 volt single phase 15 and 20 ampere receptacles located within 6 feet of the outside edge of a bathtub or shower stall must have GFCI protection. No receptacles are permitted to be located within bathtub and shower spaces, but they are permitted to be located outside of those spaces with no minimum distance requirement. A person in a shower or bathtub could reach a receptacle that is less than 6 feet from the outside edge of the shower or bathtub, and by doing so would create a shock hazard. Garage and accessory buildings. To protect people, GFCI protection should be installed at all 125 volt, single phase, 15 or 20 ampere receptacles installed in garages and grade level portions of unfinished accessory buildings used for storage or work areas. Even a tool shed or a storage shed must have GFCI protection. Where an appliance, such as a food freezer or refrigerator, is plugged into a receptacle in the garage, that receptacle must be GFCI protected. In the past, there was an exception for an appliance that caused nuisance tripping of the GFCI, but this exception is no longer allowed. Outdoor GFCIs. There must be at least one receptacle outlet installed outside at the front and back of the house that has direct access to the ground surface, and those receptacles must be readily accessible from the ground surface and not located higher than 6 feet 6 inches above the ground surface. To protect people, GFCI protection must be installed at all 125 volt single phase 15 and 20 ampere receptacles installed outdoors. The exception for GFCI protection is for outdoor receptacles that are not readily accessible and are used for temporary or non-permanently installed snow melting equipment powered using a dedicated circuit. A receptacle installed outdoors should have an enclosure for the receptacle that is weatherproof when the receptacle cover is closed and an attachment plug is not inserted. Outdoor deck outlet. Balconies, decks, and porches that are accessible from the inside of the house are required to have at least one receptacle outlet installed within the perimeter of the balcony, deck, or porch. This receptacle must be located no higher than 6 feet 6 inches above the surface of the balcony, deck, or porch. All outdoor receptacles, including those at the balcony, deck, or porch, are required to be GFCI protected. Laundry. To protect people, ground fault circuit interrupter or GFCI protection should be installed in laundry rooms with 125 volt single phase 15 and 20 ampere receptacles. This includes receptacles used for laundry appliances. There are areas in the laundry room where people can contact grounded conducting surfaces, grounded water piping, and grounded appliance housings. A hazard may exist where people put themselves between a voltage source and a grounded object or surface. Crawl space. To protect people, GFCI protection should be installed at all 125 volt single phase 15 and 20 ampere receptacles in the crawl space when such place is at or below grade level. The 120 volt lighting outlets located in the crawl space should be GFCI protected too. If there is a receptacle in the crawl space, it must be GFCI protected. Unfinished basement. To protect people, GFCI protection should be installed at all 125-volt, single-phase 15 and 20 ampere receptacles installed in unfinished basements. Unfinished basements are defined as portions or areas of the basement not intended as habitable rooms, such as storage or work areas. The exception would be a receptacle supplying only a permanently installed fire alarm or burglar alarm system. Kitchen. To protect people, GFCI protection should be installed at all 125-volt, single-phase, 15 and 20 ampere receptacles that serve countertop surfaces. Any countertop receptacle, even in an area far away from the kitchen sink, is required to be GFCI protected. Kitchen dishwasher branch circuit. In the kitchen, people may create a shock hazard by putting themselves between a voltage source and a grounded surface or object such as a dishwasher. GFCI protection must be provided at branch circuits that supply dishwashers, whether the appliance is hardwired or cord and plug connected. A GFCI type circuit breaker or a GFCI receptacle device can be used. It is common to find a single, not duplex, receptacle for the dishwasher mounted in the back of an adjacent kitchen sink base cabinet. This allows the dishwasher to be slid in and out of the cabinet space. It is good practice to provide a single, not duplex, receptacle for the dishwasher so as to discourage occupants from using an open receptacle mounted inside a cabinet. Indoor damp and wet locations. Receptacles installed in indoor damp and wet locations must be GFCI protected. A damp location is protected from weather and not subject to saturation with water or other liquids, but subject to moderate degrees of moisture. Examples include partially protected locations under canopies, marquees, roofed open porches, and interior locations subject to moderated degrees of moisture, such as some basements, some barns, and some cold storage buildings. Damp, protected. A wet location is underground or in concrete slabs or masonry in direct contact with the earth. Wet locations are also subject to saturation with water or other liquids and, in unprotected locations, exposed to the weather. Water is dripping, splashing, or flowing. Wet, unprotected. Sink. To protect people, GFCI protection should be installed at all 125-volt single-phase 15 and 20 ampere receptacles that are located within 6 feet of the top inside edge of the bowl of a sink. This applies to all sinks in the kitchen sink, laundry tub, bar sink, utility sink, garage sink, etc. And the GFCI protection is for all laundry receptacles, including the ones used for appliances. Receptacles should not be installed in a face-up position on the countertop or work surface. Boathouse. To protect people, GFCI protection should be installed at all 125-volt, single-phase, 15 or 20 ampere receptacles installed in boathouses. Boat hoist. To protect people, GFCI protection should be installed for outlets supplying up to 240 volts at boat hoists. Electrically heated floors. To protect people, GFCI protection should be installed at electrically heated floors in bathrooms, kitchens, and in hydro massage bathtub, spa, and hot tub locations. GFCI locations. GFCIs should be installed in readily accessible locations. Testing GFCI circuits. Many common circuit testers will not be able to trip a GFCI installed on a 2-wire circuit, as most testers actually trip a GFCI by creating a partial fault to ground. Obviously, if there is no ground to energize, then the neutral will not be able to sense any voltage drop. The manufacturers state that their equipment should be tested by using the test and reset buttons on the breaker or receptacle. However, many inspectors usually check them with their GFCI receptacle tester. Some testing devices check not only that they trip, but also measure at what voltage they trip. However, the best way to test a GFCI is by using the button on the breaker or receptacle itself as recommended by the manufacturer. Equipment grounding is not necessary for a GFCI to function properly. The grounded person becomes the equipment grounding conductor, and the current going through them creates the imbalance that trips the GFCI. This is why GFCIs are allowed to replace open ground receptacles without adding an equipment grounding conductor. Any breaker or receptacle that fails to trip and reset properly should be reported as a defect and written in the report as in need of correction by an electrician or qualified contractor. AFCI, Arc Fault Circuit Interrupter. History of AFCIs. AFCIs were developed in response to a need for equipment to sense when an arc fault was occurring. AFCIs were first mentioned in the 1999 revision of the NEC. It required that bedroom receptacles were to be protected by AFCI breakers. Studies of building fires had attributed many electrical faults to an arcing type, which were igniting flammable materials within the building structure. The Consumer Product Safety Commission, or CPSC, asked the electrical industry to look at a technical solution to the issue of preventing fires by tripping circuits that were exhibiting power fluctuations due to arc faults. AFCIs are able to detect faults as low as 5 amps peak for series arcs and 75 amps peak for parallel arcs. They can also detect arcing caused by faults such as dead shorts due to nails and screws through conductors, and arcing due to loose connections anywhere in the circuit. AFCI and GFCI protection. A combination type arc fault circuit interrupter should be installed to provide protection at all branch circuits that supply 120 volt, single phase, 15 and 20 ampere outlets installed in kitchens, family rooms, dining rooms, living rooms, parlors, libraries, dens, bedrooms, sunrooms, recreations rooms, closets, hallways, laundry areas, and similar rooms or areas. Where branch circuit wiring is modified, replaced, or extended, the branch circuit should be protected. Please refer to Section E3902 of the 2021 IRC that relates to GFCIs and AFCIs. GFCI protection is recommended for the following: 15 and 20 amp kitchen countertop receptacles and outlets for dishwashers, 15 and 20 amp bathroom and laundry receptacles, 15 and 20 amp receptacles within 6 feet of the outside edge of a sink, bathtub, or shower, electrically heated floors in bathrooms, kitchens, and hydromassage tubs, spas, and hot tubs, 15 and 20 amp exterior receptacles which must have GFCI protection except for receptacles not readily accessible that are used for temporary snow melting equipment and are on a dedicated circuit, 15 and 20 amp receptacles in garages and unfinished storage buildings, 15 and 20 amp receptacles in boathouses and 240 volt and less outlets at boat hoists, 15 and 20 amp receptacles in unfinished basements, except receptacles for fire or burglar alarms, 15 and 20 amp receptacles in crawl spaces at or below ground level, and 15 and 20 amp receptacles in indoor damp and wet locations. GFCIs and AFCIs must be installed in readily accessible locations because they have test buttons. GFCIs and AFCIs must be installed in readily accessible locations because they have test buttons that should be pushed periodically. Manufacturers recommend that homeowners and inspectors test or cycle the breakers and receptacles periodically to help ensure that the electrical components are working properly. AFCI protection is recommended at 15 and 20 amp outlets on branch circuits for kitchens, family rooms, dining rooms, living rooms, parlors, libraries, dens, bedrooms, sunrooms, recreations rooms, closets, hallways, laundry areas, and similar rooms or areas. Similar rooms or areas must be protected by any of the following: 1. a combination type AFCI installed for the entire branch circuit. The 2005 NEC required combination type AFCIs, but before January 1, 2008, branch feeder type AFCIs were used. 2. A branch feeder type AFCI breaker installed at the panel in combination with an AFCI receptacle at the first outlet box on the circuit. 3. A listed supplemental arc protection circuit breaker, which are no longer manufactured, installed at the panel in combination with an AFCI receptacle installed at the first outlet where all of the following conditions are met. The wiring is continuous between the breaker and AFCI outlet. The maximum length of the wiring is not greater than 50 feet for 14-gauge wire and 70 feet for 12-gauge wire, and the first outlet box is marked as being the first outlet. 4. A listed AFCI receptacle installed at the first outlet on the circuit in combination with a listed overcurrent protection device where all of the following conditions are met. The wiring is continuous between the device and receptacle. The maximum length of the wiring is not greater than 50 feet for 14-gauge wire and 70 feet for 12-gauge wire. The first outlet is marked as being the first outlet, and the combination of the overcurrent protection device and AFCI receptacle are identified as meeting the requirements for a combination type AFCI. 5. An AFCI receptacle and steel wiring method. 6. An AFCI receptacle and concrete encasement. AFCI recalls. Like many new technologies, the introduction of AFCIs was not trouble-free. In particular, Square D was forced to recall 700,000 breakers due to faults. These breakers were manufactured with a blue test button. As there are still many of these out there that have not been replaced, the home inspector should pay special attention to blue button Square D breakers and advise the client that they may be subject to recall. Testing AFCIs. When testing AFCIs, as when testing GFCIs, it is recommended by the manufacturers to use the test function on the breaker. However, this only tests the internal circuit board rather than emulates any actual fault. Many inspectors are now purchasing specialist testers that simulate an arc fault within the tester. Home inspectors purchase both AFCI and GFCI branch circuit testers. They are as common and easy to use for a home inspector as a flashlight. Lighting circuits. Lighting requirements. All habitable spaces are required to have a source of light. What is less commonly understood is that any area used for storage must also be lit, and any area that houses mechanical equipment must have illumination too. General requirements. All habitable storage and mechanical locations require light. However, some require a fixed wall or ceiling light, while others may have just a switched lighting circuit to control table lamps, etc. The inspector should also be aware of the concept of the lit path. One should be able to walk into any home in the dark and be able to go from one room to the next in a lighted path, switching each light off behind as they leave a hall or room. This is for obvious safety reasons, and as home inspectors are normally inspecting homes in the daylight, checking for safe light is often forgotten. Fixed lighting. Many locations are required to have fixed luminaries or lights. These include kitchens, bathrooms, hallways, staircases, attics, storage spaces, and at exterior doors. Staircases. These should be a special consideration for the home inspector, as any staircase with 6 or more risers should have 3-way switches at both the top and bottom of the run. Many people do a lot of head scratching when trying to figure out how 3-way circuits work. In any 3-way circuit, there are 2 potential supplies, or travelers, to the light, with each of them switched. When both switches are in contact with one of the travelers, the light is on, but when each switch is in contact with only one traveler, then the light is off. Switched receptacles. Switched receptacle circuits are allowed for all other locations, such as living rooms, dining rooms, studies, family rooms, bedrooms, and crawl spaces with mechanical equipment. Switch evaluation. All switches should be evaluated for missing cover plates, damaged cover plates, missing screws, loose installation, loose or worn out contacts, and any signs of arcing. Problem lighting. There are several potential problems with lighting to check for. Bathroom, bathtub, and shower areas. No parts of cord-connected luminaries, chain cable, or cord-suspended luminaries, lighting track, pendants, or ceiling suspended or paddle fans shall be located within a zone measured 3 feet horizontally and 8 feet vertically from the top of the bathtub rim or shower stall threshold. Bathroom luminaries. Unless recessed and listed for damp and or wet location, no luminaire is allowed to be within 3 feet of the sides or within 8 feet above any tub or shower enclosure. Ceiling fans. Many times we will see a ceiling fan wobbling around on its mount or doing a helicopter impression as it flies around its axis because it's been installed on a standard ceiling box. Remember that fixtures under 35 pounds must be mounted to a box rated for fan support, and fixtures over 35 pounds cannot be supported by the electrical box at all. Bathroom. Lighting tracks, hanging light fixtures, and ceiling fans are not allowed with the tub or shower space, which is a zone 3 feet horizontal by 8 feet vertical above the threshold of a shower or the rim of a bathtub. Recessed or surface-mounted lighting fixtures are allowed in this zone if they are labeled for use in damp locations. If the fixtures might get wet from shower spray, they must be marked for use in a wet location. A switch must not be installed within a wet location in a tub or shower space unless it is installed as part of a listed tub or shower assembly. A surface-mounted switch located in a damp or wet location must be enclosed in a weatherproof enclosure. A flush-mounted switch in a damp or wet location must be equipped with a weatherproof cover. Cord-connected luminaries, chain, cable, or cord-suspended luminaries, lighting track, pendants, and ceiling suspended or paddle fans must not have any parts located within the tub and shower zone, which is an area measured 3 feet horizontally and 8 feet vertically from the top of a bathtub rim or shower stall threshold. This area is all-encompassing. It includes the space directly over the tub or shower. Luminaries within the actual outside dimension of the bathtub or shower to a height of 8 feet vertically from the top of the bathtub rim or shower threshold must be marked for damp locations. If the luminary is subject to the spray of a shower, it must be marked for wet locations. A receptacle installed within or directly over a bathtub or shower stall is not permitted. That is a defect and safety hazard. Recessed lights. Lights in contact with insulation should be IC rated. If not, they should have 3 inches of clearance away from insulation or any other combustible surface or material. Closet lights. Open incandescent lamps or bulbs are a bad idea near storage shelving as the heat generated can easily start a fire. Protected incandescent bulbs should be no closer than 12 inches to the shelf space. Fluorescent or recessed lights should be no closer than 6 inches to the shelves. If an incandescent bulb were to be illuminating a closet space installed too close near a shelf with clothing stacked on it, these bulbs put out enough heat to set fire to cotton and other materials. This is a hazardous situation.